Assalamu alaikum. I'm going to explain to you how to perform this experiment on using MATLAB and has MATLAB for this part. So first of all, the objective number one is to study the startup dynamics of reaction in a CSTR. So our reaction is this: propylene dioxide reacts with water to give propylene glycol. Okay. So this we will study in a CSTR. So we want to simulate the dynamics, how we start. So the informations are given here. This is the reactor. So initially, how we simulate, the reactor is filled with water. Then we add water again and the ethylene dioxide. Okay. So this is unsteady state. So we have all the models, unsteady state models here with the initial condition. As you can see, we start with the water. So water is already there. Concentration is this much. Okay. So unsteady state mode balance, unsteady state energy balance. So all of this differential equation, ordinary differential equation, we will model it in MATLAB. So I have given you the MATLAB code. So this is the MATLAB code, and you can see first line function dy virtual experiment to t comma c. C is a vector which contains c1, c2, c3, c4, c5. So c1 is the reactant for the oxide, and c2 for the water, c3 for the inert, and C3, okay, let's see here, and C5 is for the temperature. Okay, so we want to get the profile, starter profile for temperature and the concentrations. Okay, so what you do, yes, you take this code to MATLAB. This is a functional file. Take to MATLAB, open a new script. Okay, save this in MATLAB folder. I have it already, so I will replace this. Okay, so this one is here, everything is here. The TA1, the coolant temperature is 15 right now, okay, which is fine. And then so you have this differential equation, set of differential equation 5 here. Okay, so now to solve this, we need to type in command window this one. We go to command window, and type this one, OD15S virtual experiment 2. This is time slot. This is the initial condition. Okay. Okay. So after typing this code, if it doesn't come anything, it's working. So now if I wanted to plot T comma C, 5 is the temperature, fifth one. So that gives me the temperature profile. Yeah, here you see, this is the temperature profile starting with 25 the water temperature was 25. Reaction starts, so reaction is exothermic. It goes to a peak. We have the coolant, but in this region the reaction is dominating. So after the coolant start working, it brings down the temperature to 70 and make it stable. So this is the temperature profile. Okay, and we can get the concentration of reactant. The first one, the oxide, which is 1. Okay, here it is. This is for the oxide. So initially it is, we are adding, so just accumulation is going on. Reaction is not there, or reaction is there but it is not dominating. Only the mass transportation, mass transfer is coming. So like ethylene oxide is coming, is accumulating, then it start decreasing. So here reaction takes the control. After sometimes it is steady, so it becomes stable. So this is the concentration after steady state concentration. Okay, so this is about the profile of temperature and concentrations of the reactant. And then this is the startup. So this one is enough. If you want to plot the product, which is C3, I guess. Yeah, so you can see this is the product. It will increase, the glycol increase and then become stable. So this is the first part, which is studying the effect of give the startup dynamics of the reactor. Next, one thing is there to study the effect of inlet coolant temperature by changing the cool water. So if for the same one, concentration is there, so I will use hold on. Okay, and then in the main program change the coolant water. So coolant TA1 was 15. Let's make it 5. Save it. Go to the command window. Run it again. The program, run it again. That command, yeah, this one is now 15. Okay, it is done. So now just plot temperature. This is the temperature. Okay, so okay, right now I have only one. This one I will use hold on and then change the TA to 15. Okay, the coolant temperature. Again go to the command window and run the code again. Then run the now get the temperature again. See, I should have two graphs. Yes, the one is the 15, the first one. The first one was 5. Okay, let's use the temperature legend. The first one we run it for 5. TA equal 5 degree centigrade, and then TA. Okay, this one TA, and this is the TA. TA equals 15. It will show now clearly. Yes. So the blue one is 5. So when we have higher, lower coolant temperature, it will cool down the reactor more. So the final temperature is less, which makes sense. Okay, and then the other one is the red one. when we have the higher temperature of the coolant, it makes the higher temperature of the reactor. Okay, so in order to study the effect of coolant temperature, you can present this graph. Okay, how to copy this? Edit, copy figure, and then you can take it to the Word like this. Okay, so we can also repeat the same thing. Click hold off because we want the concentration now. Okay, close this. Right now the temperature is 15. Okay, this is fine. We can plot the concentration of A. Okay, 15 with 15. Hold on again. Now I change this to 5, the coolant temperature. Save and run the code again. Run the code again. This one. Okay. Now the plot what? The concentration of reactant, the first one. I have only one here. Okay. Okay, hold on, I will use, and then again change to 15. Then run it again. Plot. Yes. Now I have two. So one of them for 15, one of them for 5. This one, the last one is for 15. Okay. So first one was 5 and then 15. So let's use the legend. We give them, 5 and 15. Okay, this is fine. So see the graphs. 5 and 15. At high temperature, higher coolant temperature, your reactor temperature is higher, so conversion is more. So the reactant temperature, the oxide is less. It is being consumed more. At at the lower coolant temperature, the reactor temperature is less, so conversion is less. So concentration of reactant is high. Okay, so this way you study the effect of coolant temperature, and that's it for the MATLAB part.